Welcome to this explainer. Today we're looking at a concept that honestly feels a bit like science fiction, but it is rooted entirely in real-world thermodynamics. We're going to explore the absolutely mind-bending idea of generating actual physical ice alongside thriving ecological biomes right in the middle of the scorching Texas heat. And you know what the most incredible part of this is? We're going to do the whole shebang using zero grid power. This isn't just some cool science experiment either. It's literally a blueprint for the future of sustainable living, crushing those massive utility bills, and surviving extreme weather.
I want you to picture something for a second. Imagine the absolute oppressive heat and humidity of a Texas summer. Now imagine walking right out of that heat into a shaded pavilion and getting hit with a blast of perfectly chilled dry air. Imagine reaching into a dispenser, grabbing a block of solid ice, and looking around to see cold water streams flowing right by you. Sounds pretty impossible, right? How on earth do we orchestrate a freezing oasis without firing up massive, energy-hungry mechanical compressors? Well, I am absolutely thrilled to share the science with you today, because the secret to cooling down actually lies in looking straight up.
Okay, let's dive into the foundational physical principle that validates this entire premise: passive radiative cooling. So heat naturally wants to flow from warmer objects to cooler ones. What this process does is passively redirect the ambient heat around us straight out into deep space. It's completely passive. It requires absolutely no electricity. The whole thing relies on tuning materials to very specific optical wavelengths so they can essentially dump heat directly into the cosmos.
So here is our roadmap for today. First, venting heat to deep space. Second, engineering a microclimate. Third, the power-free ice tower. Fourth, hydronic cooling for homes. And finally, the ecological thermal cascade.
Let's jump into Section 1, venting heat to deep space. To figure out how we cool Texas down, we first have to look straight up into the cosmos.
Deep space is, practically speaking, the ultimate thermal garbage dump. It's this massive thermodynamic heat sink sitting at an unfathomably cold 3 Kelvin. To put that into perspective, that's roughly negative 454 degrees Fahrenheit. So yeah, quite a bit colder than your office air conditioning in January. Now, Earth's atmosphere normally traps most thermal radiation, which is great because it keeps us warm. But there's a loophole here. The atmosphere has a specific, optically transparent band right between 8 and 13 micrometers. We call this the atmospheric window, and it basically acts like an open pipeline straight through the sky. If we use materials tuned specifically to radiate thermal energy within that exact 8 to 13 micrometer band, that energy passes straight through the atmosphere without getting absorbed. And we can actually pull this off using specific crystalline structures. Think dielectric crystals like quartz and sapphire, phase change materials like vanadium dioxide, and highly engineered photonic crystal nanostructures. These crystals are the real enabling technology here. They're what allow us to shoot our ambient heat directly into that deep space heat sink.
Moving on to Section 2, engineering a microclimate. Because, let's be real, venting heat straight up doesn't do us a lot of good if the ambient wind just keeps blowing hot air right back at us. We have to apply this crystal technology on the ground to create a localized thermal refuge. Cooling down an entire open-air region is next to impossible thanks to fluid dynamics and atmospheric physics. So instead, we build a microclimate. We take the specific Texas climate challenges and counter them with targeted architectural solutions. To fight that high Gulf Coast humidity, we use a vertical condensation tower that reverses evaporative cooling, essentially wringing the moisture right out of the air. To combat the intense daylight radiation, a photonic crystal roof canopy reflects over 95% of sunlight. And to stop those hot ambient breezes from just blowing all our cold air away, we use a sunken ground grade combined with low emissivity windbreaks. Put it all together, and these structural countermeasures depress internal effective temperatures by 10 to 18 degrees Fahrenheit below whatever is happening outside.
What's really fascinating about this is how these materials act completely autonomously. Take the radiative sky canopy, which is made of silicon dioxide and aluminum oxide nanostructures. It constantly reflects sunlight while radiating heat. But the dynamic valve roof made of vanadium dioxide, that is a real game changer. This phase change crystal acts as a literal thermal valve. It automatically opens up its infrared emission whenever ambient temperatures cross 25 degrees Celsius, and then it just switches itself off at night to prevent overcooling. There's zero human intervention, no electrical switches. Just pure physics, fully enclosed in IR-transparent polymers to keep that perfectly cooled air from blowing away.
All right, Section 3, the power-free ice tower. Let's look at the mechanical heart of this operation, which relies entirely on gravity-driven cooling to go from just chilling the air to generating actual ice.
294 kilopascals. That is the hydrostatic pressure generated by a standard 30-meter municipal water tower. By placing our thermal hub at the very highest elevation, we're letting gravity do all the heavy lifting for us. We've got pre-cooled water sitting all the way up at the top, creating a massive amount of downward hydraulic pressure.
Now, to drop our working fluid down to 0 degrees Celsius, literally freezing, we need rapid thermal expansion. And we've basically got two mechanical choices to make that happen. If we go with the Joule-Thomson throttling valve, which relies on passive free expansion, we'd need an immense 6,000 kilopascals of pressure. That would require an ultra-high 611-meter tower, which is just completely impractical. But if we use an isentropic turbo expander, which extracts mechanical work to rapidly drop temperatures, we only need a 25.08 kilopascal drop. Since our 30-meter tower is already giving us 294 kilopascals, this is highly feasible. Mathematically speaking, the turbo expander is absolutely the only sound choice for this system.
And here is where the magic happens. Deep underground in the subterranean ice vault, we run 10 micro-turbo expanders simultaneously right off that water tower's pressure. This freezes the harvested atmospheric water directly onto vertical stainless steel plates. We can even use gravity chutes to drop 10-kilogram blocks of ice right into a community kiosk. This vault acts as a high-density thermal storage bank, keeping everything at 0 degrees Celsius and safely anchoring the entire property.
Section 4. Hydronic cooling for homes. Now that we have bulk ice, we've got freezing meltwater, let's follow this 4 degrees Celsius water as it leaves the ice vault and travels downhill for distribution and safety in the residential and laboratory sectors.
Think about it. If you just pump 4-degree water straight into the floor of a house in humid Texas, that floor is going to instantly sweat from condensation. And nobody wants an indoor slip and slide, right? This brilliantly illustrates the delicate balancing act we need. So we use precision hydronic valves. The PRV 101 steps that intense gravity pressure down to a safe 150 kilopascals. Then, the TCB 201 valve acts like a blender. It mixes the freezing 4-degree supply with warmer 18-degree return water to create a perfectly safe 12-degree supply for the home slabs. And just in case, there's the SV203, a fail-safe dew-point solenoid that instantly shuts off the flow if indoor humidity ever creeps over 65%.
With the condensation threat totally neutralized, this heavy chilled water flows through robust PEX loops embedded right into the foundation slabs and the lab walls. When you combine that with the dry, chilled downdraft air ducted in from the condensation tower, it completely replaces mechanical air conditioning. It maintains a perfect 21 degrees Celsius, which is about 70 degrees Fahrenheit, indoors entirely off-grid. Imagine entirely eliminating your summer AC bill while staying perfectly, comfortably cool.
Finally, Section 5. The ecological thermal cascade. We've cooled the air, we've made ice, and we've air-conditioned the homes. But what happens to the wastewater after it leaves the buildings? Well, prepare to have your mind blown by these ecological biomes. The crucial thing to remember here is that this water is on a continuous downhill journey, both in terms of elevation and temperature. It starts at the 15-degree tower, hits freezing in the ice vault, then warms up slightly as it cools the homes. By the time it exits the residential cooling loops, it's sitting somewhere between 10 and 14 degrees Celsius. Now, that's too warm to cool a house anymore, but it is the absolutely perfect temperature to cascade into a series of ecological biomes.
So, the very first stop for our 10 to 14 degree runoff is a cold water salmon raceway. Because the water is still incredibly cold, it retains a massive amount of dissolved oxygen. We're talking over 9 milligrams per liter. On top of that, the sheer volume of water flowing out from the ice vault acts as this huge thermal buffer against the baking Texas afternoon sun. We are literally breeding cold water salmonids in a sweltering southern climate, using nothing but the structural runoff. How cool is that?
After visiting the salmon, the water warms up to about 18 to 24 degrees Celsius and spills right into a massive polyculture lake. This lake receives all the nutrient-dense effluent from the fish, which acts as fertilizer. It feeds these thick, floating biomats of azolla and duckweed. These plants are incredible because they pull and fix nitrogen directly from the atmosphere. They yield up to 40% crude protein by dry weight, making amazing animal feed. Plus, that dense plant cover shades the water, suppressing evaporation by up to 50%, which keeps the bottom of the lake cool enough for catfish and tilapia to thrive.
Finally, the water reaches ambient temperatures of about 20 to 26 degrees Celsius and spills into a terminal retention basin.
And here, a small beaver population takes over. Their dams turn this final runoff into a self-maintaining engineered wetland. It naturally filters out sediment, it stabilizes the water table, and it recharges the local aquifers. What started as just a passive alternative to a home air conditioner blossomed into this vibrant, endlessly expanding biome of biodiversity.
This quote really hits the nail on the head. Modern survival doesn't require fighting nature with grid power. It requires orchestrating natural physics to do the work for us. By using crystals to vent heat to space, leveraging gravity and water pressure to make ice, and then intelligently cascading that thermal energy downhill, we literally turn a harsh environment into an engine of life.
We've seen exactly how this system can conquer the scorching humidity of the Texas Gulf Coast completely off-grid. But I want to leave you with this thought today. If we can engineer this level of extreme thermal control and ecological abundance in Texas, what other harsh, unforgiving environments could this passive thermal cascade completely transform next?